Yeah, thank you. So, okay. All right, I just want to make an advertisement for a new review in particle data group on machine learning. Most of the topics on machine learning and its applications to, mostly also cosmology and so on. So it's maybe a nice review for the audience. And it's written by myself, Kyle Kramer, and Kazu Terao. All right, so let me talk about my talk today. It's going to be mostly about cosmological applications of normalizing flows, but I'll also talk a little bit about statistical physics application. And I'll talk about two different types of flows that can be actually combined together. And I'll start first with what we call translational and rotational equivariant normalizing flows. All right, so before I do that, I want to introduce how we do analysis in cosmology. We would like to model the data likelihood, which is probability of the data given some parameters. And from this, assuming on the parameters, we can get a posterior on those parameters. So in the Gaussian case, this can be written analytically. It is, however, computationally expensive, even in that case, to implement it. In the non-Gaussian case, people, what you usually do in cosmology is they come up with some summary statistics. For example, we talk about power spectrum, we talk about eye spectrum, we talk about halo mass function, void, with all sorts of statistics. So when you have those, you can combine them in so-called likelihood-free inference way, which is you literally distribution of the statistics. Typically, we model it as a Gaussian, and we need to compute the variance matrix of all those summary statistics. So first of all, this is actually computationally quite expensive. This so-called likelihood-free inference method is very expensive because you have to model this summary statistic for every cosmological parameter. And second, there's no guarantee that you have not lost information. Right? If you only model the power spectrum, well, maybe there's in the 3-point function that you haven't included, right? Okay, then maybe there's information 4-point function, so on and so forth, right? So it's very hard to have any confidence that you have actually the amount of information with this method. That there are two ways actually how to do optimal analysis. One is actually doing still likelihood analysis, but doing called implicit likelihood, where you have to write down the likelihood of your initial conditions. You have to do this marginal integral and so on and so forth. I'm not going to go into that. This is something that we are actively pursuing, but it is in a million. It's very expensive to do, and the results have been, let's say, slow going. So this is why I'm going to talk about an approach today, which is let's try and maybe learn directly the likelihood using machine learning tools. Now, learning likelihood, what is the likelihood? The density, conditional density. So in other words, it's the density, probability density of the data, given some parameters, in this case, cosmological parameters. This data are often in millions or even billions of dimensions, okay? So we can measure millions of galaxies in their positions, and we therefore have information from millions of galaxies these days. But it's even more complicated, right? Because if you try to discretize this and do pixelized density estimation of the galaxy, you actually typically to do this in 10 to the 9 dimensions, for example, 1,000 cubes. So this is very expensive. This is a very high dimensional problem. And the question is, can we learn the densities in such high dimensions? Learn the densities using normalizing flows, and the only hope to make this visible is so to reduce basically the number of degrees of freedom in high dimensions. So, all right, what are normalizing flows? We've seen a few times already. I'm not going to go into details. All right, I can go back, right? Okay, so typically what we're trying to map trying to map to some simple probability distribution like a Gaussian with univariance and zero mean. And if you try sample from this, then through this flow, you actually get to some complicated probability distributions. And in high dimensions, these complicated probability distributions actually can be samples of the data or simulated data. I'll show an example of that. Okay, in 1D, this is very easy. For example, suppose that this is the target density, and you're trying to learn some mapping to the Gaussian. Maybe you start with something like this. This is not very good yet, but then, you know, if this function f features, you fit for them, and in the end, maybe you get something like this, and this maps this probability distribution to this. Okay, so how do we do this in cosmology? As I said, we need to take advantage of the symmetries. And what we're going to do is, let me skip this. How are we going to parameterize? All right, so let me get now to this TRENF, translation rotational equivariant normalizing flow. So we're going to take the idea of translation invariance similar to convolutional neural networks, which is basically we're going to take the translation equivariance by doing actually Fourier transforms. Okay, so convolution theorem tells us that convolutions are translation equivariant, and so the translation equivariance is going to be used in Fourier space by using Fourier space, and then we're going to enforce rotational symmetry. Let me explain how. All right, so what we're going to do convolution in real space after the Fourier transform becomes a product in Fourier space. And so what we're going to learn is this what we call transfer functions, T of K, but we're going to also enforce rotational symmetry by simply making these functions here a function of the wave vector length only, and not a function of its direction. Okay, so this is a vector, this is a scalar. So this is what we are learning. We're going to have machine learning to learn this using the standard loss, which is maximizing the likelihood. And then, so this is how we're doing the convolutions. And then we also need to put in nonlinearities. And so here we have basically a general nonlinear function. So this is not a ReLU or something like that, general nonlinear function that has to be invertible and differentiable. And we use splines for this. So this is a one-dimensional function, so that makes it very easy. So this function basically applies to these convolutions and looks for the most non-Gaussian convolution. Once we find the most non-Gaussian convolution, we map it to a Gaussian. Okay, and this is we have done one layer of this normalizing flow. And then we can go and search for different convolution that still has some non-Gaussian distribution, and then we Gaussianize that. All right, so this is how we build our flows, and this is how we build layers into a deep network. Yeah. As I said before, millions, billions. You know, this is very high dimensional. X. Yeah. No. These are all fixed. Yeah. Normalizing flows, by the way, also, you know, they don't change the dimensionality. Yeah, normalizing flow is always the same dimensionality, right? So that you can actually build a Jacobian and you can build a density. Yeah. So this is how we put together the deep model, right? So these are the operations. Both convolutions are easy to write on the Jacobian, and the nonlinearity is just a derivative, one-dimensional derivative. So this is our Jacobian here, and then we put together several of these layers. Okay, so what is good about this is there's no need for data augmentation because we have built the symmetries in. In principle, this can have very few parameters. So what are number parameters? They're these transfer functions. They have function of wave vector length only, and they're smooth, right? So they can, per layer, they will be modeled by a few, you know, let's say splines. And the same is true for the nonlinear function. Nonlinear function is one-dimensional. It's modeled by a few spline nodes, and so really, what ends up being the total number of parameters is for 100 or a few hundred. All right. This means there's less overfitting because there are very few parameters to fit, and better generalization. Now, of course, this point, of course, is controversial, right? Because we know that even high-dimensional parameterizations, large parameterizations can avoid overfitting, but at least in principle here, taking advantage of the symmetries really does reduce the number of parameters. And the results are physics consistent in the sense that they have symmetries built in. All right, so the other thing, what we do, we need to do this conditionally as a function of cosmological parameters. Here we use standard, hypernet kind of thing. So the conditional dependence is built using standard neural networks. All right, so let me show some results, some experiments. These are n-body simulations of cosmological models. We're going to be varying two cosmological parameters, matter density, omega m, and the amplitude of fluctuation, sigma 8. We use an n-body solver for the training. And we're going to model this with a 5-layer TRENF. Okay, and so here are the results now of the samples, how the samples look like. Varying here the amplitude fluctuations. So basically, when the amplitude is small, then the fluctations are, as you can see, smaller, and then get a lot sharper and more nonlinear as we increase this parameter. And here is omega matter. And what happens if you vary omega matter is that as we go to yeah, please, yeah, pixels, yeah. Sorry, this was 512 square. Yeah. Well, these are projected n-body simulations. These are projected density of dark matter. Yeah, right, yeah. TRENF takes into the images. Yeah, so the data, for example, this could be applicable to weak lensing data, for example. They are like really two-dimensional projections of dark matter. All right, so the other thing one can look at is how the distribution looks like in latent space. Here's an example of this. If you map this through correct cosmology, you get something that really looks like white noise, because this is what latent space is supposed to be, white noise. So that means zero mean unit variance. So this is the PDF, but even if you look at this by eye, it looks like there are no correlations seen. So in other words, our eye can also act as some sort of neural network, I guess, to identify if there's anything obvious in terms of non-Gaussianity. For example, if you pass this through using incorrect cosmology, so in other words, using wrong cosmological parameters, then you actually do start seeing that this is not a perfect white noise Gaussian distribution. You get artifacts that look here. You can see some correlated features here and stuff like that. Sorry. Yeah, this is the data, let's say. This is passed through the normalizing flow, right? No, a normalizing flow is supposed to map the data into a white noise Gaussian, right? So this is what is shown here. Oh, these. Yeah, right. This is just one distribution. Yeah, this is just 1-point distribution. Yeah. No. This is just 1-point distribution function. But let me show you on the next slide. Let me show you on the next slide. Okay, so now the question is, well, is that really non-Gaussian field? By eye looks, sorry, is that really Gaussian field? By eye looks Gaussian. We can do 1-point distribution and compare it to a Gaussian. There's, we see perfect agreement. We can do power spectrum, which should be white noise. And again, it's completely white. And we can do 3-point function and should be 0 because it's a Gaussian field. And again, it's completely 0 here, right? So these are the tests you can do in latent space rather than in data space, right? So that's, if you start seeing some deviations in latent space, then maybe you're not doing a perfect job. And that's the advantage of this thing. So you can do something, some non-parametric tests, basically. Yes. Sorry? Oh, no, these are just, the error bars you would get if you were to measure a 3-point function. Oh, you're asking what's driving the errors? This is called what we call sampling variance, right? You have to find a number of modes, so you cannot determine the skewness, for example, with the perfect accuracy. That's what's driving it. Well, increasing the volume would decrease it. Yeah. Basically, this is just this is how well you can measure this 3-point function. Anything within these errors is indistinguishable from the Gaussian. All right, but the real, I think the real advantage of these methods is in the density estimation, because one can do posterior analysis, as I mentioned earlier. If you have the likelihood of the data, you can do the posterior analysis. And in principle, if you have learned perfectly the likelihood, then you can approach what we call the optimal analysis with the smallest possible errors. Here I'm showing the results of the standard summary statistic analysis, which is called the power spectrum analysis. This is in orange. And I compare this to this TRENF analysis with the full likelihood, and it's shown in green. And what we can see is there's about a factor of 6 times smaller area of the green contours compared to orange contours. Okay, so in other words, there's 6 times more information in the full likelihood compared to just information in the power spectrum. So this is where this is huge, right? It's like, you go out and you build a telescope, and instead of 1, you have, 6 telescopes by just doing this, right? So this is why, people are very excited about these methods, because they do try to get optimal amount of information. And potentially this optimal information has a lot more information than the power spectrum alone. Okay, so the other thing that I would like to emphasize is actually very, very hard in these likelihood-free inference methods to actually get the errors correct. And here we worked very hard to get this. And star is the true answer. And these green contours are 95% contours. So in principle, only 1 out of 20 should be outside these green contours. And we have achieved this in this case. All right, but usually, getting the correct uncertainty quantification is both hard and also very hard to actually verify. How do you know you have the correct errors? So you really need to do these frequentist types of tests to convince yourself that you have the correct error contours. Okay, so let me show a statistical physics application here. We can extend this to Ising spin model, for example, where we have used a Haber-Sertonovich transformation to map discrete spins plus or minus 1 to continuous field. And then we have learned this continuous field representation using normalizing flow. Then we can draw samples, first continuous samples, and then there's another conditional probability distribution to draw discrete values plus minus 1. And this is what was done here. These are the training data of the Ising model. And this is how well we were able to learn this, at least visually. The samples look similar. Samples from the generative model look similar to the samples from the training data, which in this case were obtained from MCMC. You can see there's a phase transition roughly around 2.3 temperature. let's see. Here we did not do a full rotation invariance, right? Instead, we did what we call R, D4, right? So in other words, if you rotate the system by 90 degrees, then you get the same symmetry back. It's actually in this TRENF formalism, it's actually very easy to implement this symmetry. Okay, so what you can do with this, and so here, for example, I'm showing the results as a function of number of layers. So you can see that there's always a phase transition, but the temperature of the phase transition is varying, and then it slowly settles down with 5 layers. It settles down roughly at the correct value, which is 2.3. So if you then investigate the energy and specific heat or magnetization and susceptibility, then you see evidence for a phase transition, right? You see evidence for, you can even go and measure critical exponents and stuff and so on and so forth. Okay, so these are the possible applications of this normalizing flows to statistical mechanics problems and condensed matter. Okay, so let me now, in the remaining part, talk about another flow, which is an extension. And this is, we call it multi-scale. You can also think of it as a coarse graining normalizing flow, and explain what I mean. But let me first pose the problem. What's the problem is that if people are using these machine learning tools and they're applying to different simulations, and they don't always agree. So in other words, if you have developed a tool, machine learning tool on one set of simulations, like Illustris, for example, everything looks great. Then you apply to a different simulation, then everything looks terrible, right? So why is this happening? This is happening because there are some numerical artifacts in numerical simulations that differ between them, but usually they differ on very, very small scales. There's maybe some numerical things and stuff like that. Machine learning, of course, picks up everything, and it therefore gives us an artificially small errors, because probably these errors, this very tight ability to extract these parameters is probably not real, because who knows what machine learning was picking up, right? Maybe something on small scales, maybe something close to machine precision or whatever, right? So we need to be able to separate what is in real physics from what's numerical. All right, and so this is where I think the scale dependence comes in, because typically the models all agree with each other, simulations all agree with each other on large scales, and then as we go to smaller and smaller scales, they start to deviate from each other, both because of numerical artifacts, but also because small scale physics is unknown, for example, baryonic effects and things like that. So here's an example. For example, several simulations have been tried out, and one of them sticks out. And in other words, it hasn't, it gives incorrect cosmological parameters if you apply it to this simulation. So you can certainly try and model the systematics and remove, but even after doing that, this actually is after doing that, and still one of them sticks out. So maybe you haven't modeled the systematics perfectly, and so on and so forth. So our proposal is let's try and do normalizing flows as a function of scale, and let's try to test the results as a function of scale. And if the results start to deviate from large scale to small scales, then we have an indication of some systematic, and then we need to work harder to remove it. So how can one build normalizing flow, which is a multi-scale normalizing flow? One can adopt the concept of coarse graining. If you take the highest resolution, let's say 256 square in this case, we can first average 4 pixels together into a coarse-grained distribution, and then there are there are 4 pixels. We moved into one, which is the average, and then the other 3 we are modeling as these extra pixels. All right, and so what we're going to write then is that this probability distribution is a joint probability distribution of this coarse-grained and the extra. And now we're going to split this into probability distribution of the coarse-grained data plus the conditional probability distribution of this extra given this. Okay, so this is how we build then the flow by learning this thing first, but then this one we can split again. Right, we can add another coarse graining layer, now going from 128 to 64, and we can do exactly the same thing again. And so, all right, and we can do it again, right? And so what we do in our approach is Well, at some point, let's say 32 squares, this is small enough that we can actually model it with something else. In this case, we can model it with our TRENF, which is what I talked about earlier. So this is how we built now a multi-scale normalizing flow that really tells you as a function of information, right? So this one would be, we'll have this probability distribution, which is on the larger scales. Then we'll have this one, which is a factor of 2 smaller scales. And we'll have this one, another factor of 2 smaller scales. And finally, this one, which is another factor of 2 smaller scales. So here's an example, a toy example, right? We do 512 square, and we model it as a 64 with TRENF, and all the other multi-scales we model, all the other scales we model multi-scale flow. Same example as before, but now what we're going to do, we're going to add some unknown systematic. In this case, we just add a noise term. All right, so if you don't add a noise term, then here are the results. We have 4 different likelihoods from different scales. And you see the largest one has the largest error. And as we go to smaller and smaller scales, you see, we get smaller and smaller errors. That's because we have more and more pixels, right, on small scales. So you can see in this case, everything is working very well. But now suppose we add some unknown systematic, like a Gaussian noise. Then what is happening is that the large scales are still consistent with each other, but smaller scales are not, okay? Because of this, now we see clearly, because we split now the likelihood into 4 different components, we see clearly that there's a problem in our data. There's some perhaps unknown systematic that we don't know about, and then we can do 2 things. We can, of course, try and think about what this could be, or we can also just try to remove small scales. Right? As we remove small scales, we get consistent results again, but the errors are bigger, of course, because we have removed small scales, which on the previous plot here had the largest amount of information, and therefore the smallest errors. So that's the idea behind these multi-scale flows. It allows us not just optimal cosmological analysis, but also in some sense a robust analysis, because it enables us to investigate the effects as a function of scale, and therefore identify if we have problems on small scales. And if we have problems on small scales, then we stick to the larger scales. By the way, this is common procedure in the power spectrum analysis. We always decide that we're going to remove small scales in the power spectrum because we cannot model it. And so here you can think of this as a simple extension of this to the full likelihoods rather than just to the Gaussian. Yes. Yeah. Yeah. Yes, sorry, yeah, I skipped those slides. I have them. If you want technical details, these are actually affine transforms that we use here, so this is not TRENF at all. Okay, and we do lose a rotational equivariance. They're still convolutional, so the translation equivariance is there, but rotational is not. Okay. Yeah, I didn't talk about the details of the architecture that we're using, but we can talk about it later. Yeah. Yes. Okay. And so this is my last slide. So this method, this multi-scale flow, seems to give a factor of 2 larger figure of merit than current state-of-the-art methods in cosmology, such as convolutional neural networks or scattering transforms. So it is promising both in terms of extracting near optimal amount of information, but it's also promising in the context of robustness, in the sense that we can do these scale dependence tests and try to convince ourselves that what we're doing makes sense. we all know, a lot of people are skeptical about machine learning tools because they are, black box, and because we don't know what they pick on, right? This is an attempt to try to address that criticism and try to make it more robust in a similar vein as what we are trying to do in the standard cosmological analysis, such as the power spectrum. All right, with this, I'll stop here. Yeah. Well, as I said, weak lensing is, in some sense, a direct observable. Weak lensing maps, they're projection maps along the light cone. So I haven't shown the results here, but for example, this statement that we get a factor of 2 higher figure of merit, this statement is on realistic weak lensing simulations. Okay, so we're training on those and we're getting better results on those. Well, it is convolutional, so it still is translational, but it's not rotation. It doesn't have any rotation symmetry. Because here what we are really doing is we're learning this map conditional on this. So this is you give up rotation invariance when you try to do this. We didn't even try to do any rotation invariance here. So instead well, of course, one can always do augmentation of data and stuff like that, right? But yeah, these definitely don't have explicit rotation equivariance.
Questions?
Okay, let's wait.
I suspect this means if I had some reason to not trust the model at scale, but trust the both low and high scale, could I do that multi-parametric composition?
Yeah, in fact, well, this kind of happens here, right? You see, the smallest scale is actually this one here. I don't know if this was luck or whatever, but it's kind of closer to the truth than this one here, right? This one here is 256. So it's still small scale, but not the smallest scale. The smallest scale is the brown, right? But the one that sticks out most is the 256. The larger scales are 64. Then so this is the green, then the red, and orange, right? These are, the first three are all consistent with each other, and the contours are within, they give the correct posterior, but it's actually 256 that sticks out most. And then, as I said, for whatever reason, not fully understood, 512, it's still out, right? Obviously, it's obviously out, but it's not as
bad. Okay. Oh, great. All right, thanks.
So you can certainly do this as for any scale. Yes.
Perfect.
It's but okay. Modulo, it's a factor of 2. Right? In this architecture, it's a factor of 2 scale. Maybe because probably people can't hear.
Could you talk more about your choice? What drove your choice of machine learning architecture? Why did you choose TRENF as opposed to anything else? What is that something you chose intentionally because of some of the properties of the underlying problem?
Well, first of all, yes, cosmology, the universe is translational rotational invariant, right? So that is the underlying reason we chose this. But just to give you an example, let's say on the 2-point function, if you want to measure 2-point function, which is the power spectrum in 3 dimensions, and you want to measure it as a function of Fourier mode vector, I I don't know, let's say you're doing this in 100 bins, in each direction, it becomes 100 cube, right? It becomes 1,000,000 parameters you have to learn. If you adopt rotational invariance, then you can only do, you only need to do this as a function of the length of the wave vector. Instead of 10 to the 6, you now only have to do it for 100 parameters, 100 bins, for example. Okay, so this is why, especially in 3D, as you go to higher dimensions, imposing rotational equivariance, saves you tremendously in terms of number of parameters you need to fit. So that's the underlying reason for rotational equivariance. Rotational equivariance is typically not implemented in machine learning tools. So this is, translation, we all know convolutional networks have been around for a while, right? So this is not particularly new. And we all know that, Fourier methods are one way to implement convolutions, but rotational equivariance is, I would say, more specific to these kind of problems that we have in physics.
Okay, thank you. So I think it's time to move on. So let's thank Uros again.